Okay, I'll now turn it over to our presenter. Vali, the stage is yours.
Thank you, Ken. Good afternoon, everyone. Thank you for joining the webinar. I'm Valipan Muthukarpan. I'm a PhD candidate here at NC State University. So I'm going to talk about smart meter data analytics for transformer monitoring today. Before I jump into the project, I want to thank our team without whom this project wouldn't have been possible. Dr. Mesud Baran and Dr. Ling Lu are my advisors at NC State University. PJ Ram is a manager at Electricities who has been coordinating with APPA, who is our funding agency, and the local utility New River Light and Power. Matthew McTack and Ed Miller are with New River Light and Power. So they provided us with smart meter data and other data sources available with them, and have been providing really helpful insights that helped with our analysis. So this is the overview of the project. I'm going to talk about what is the motivation behind setting up this project and the different tools that we developed as course of this project. To start with, our US grid, or grid around the world, has been going through an aging infrastructure. So the figure here shows all the conventional power plants in US, and the red circles indicate that they have been really getting old in recent times. So this has like catastrophic impact on our environment. So this is a figure of the biggest wildfire that happened in California around 2018. And the primary cause of this wildfire was that a hook on the transmission line failed because the utility didn't pay attention to this asset. They didn't have an asset management tool, so they didn't pay attention to it. So you can see a groove here. So through friction, this groove happened over multiple years, and eventually it failed to hold up the transmission line, which fell on nearby trees and caused like the biggest wildfire in the history of California. So on the other spectrum, we have distribution systems, and they have been going through electrification. Electrification, I mean like electric vehicle charging, it's exponentially increasing. There's PV penetration from rooftop PV and utility scale PV on the distribution feeders. And then there's a changing, consumption pattern with the customers, like, especially after the COVID. You can see the transportation-based electric usage is expected to increase exponentially, after 2020. So this, along with the aging infrastructure, seems to be a big issue for utilities. So of these, assets that are available with utilities, the major, or the one we are familiar with, is transformers. And this is a figure of a power transformer, which we are really familiar with. These are installed above 100 kVA, usually installed in the transmission level. You can see they come with really fancy control, protection, and predictive maintenance technologies installed on them, because a loss of one transformer can have a significant, economical loss to a utility because it serves a large area of customers. But on the counterpart, we have distribution transformers. They supply a bunch of small customers. They are around the neighborhood. They're really like bare minimum. They don't have any protection or control devices, probably a fuse on top of them. There's no monitoring on these devices. The primary reason, because it's not economical to install these kind of monitoring devices on distribution transformers, because it doesn't make economic sense. But what they lack in value, they make up in numbers. One distribution feeder can have tens of thousands of these transformers. So if all of them start failing due to the electrification that we talked about, then the utility is going to get a lot of customer calls saying power outage, and it's going to become a big headache. So one thing that's missing on these devices, and it's of importance, is predictive maintenance, especially with electrification. So we are going to see how we can address this issue, using existing infrastructure. So when I talk about existing infrastructure, you can see there's been an exponential increase in smart meter deployment, AMI deployment around the US utilities. So, but then the issue is we have a lot of smart meter data available, but then they're not really typically used beyond billing purposes and customer analytics. So let's look at a life cycle of a data analysis, right? You go collect some data, and then you will analyze this data, and then you will eventually take some action. Then you'll realize you need more data, more granularity in the data. So you'll go back and collect more data, and then you'll do this in a loop. When it comes to utilities, they have been collecting a lot of data recently, especially with smart meters. And then there's SCADA measurements available. There are a lot of other data sets available with utilities. And then the analysis part has been lacking as well, because they're not being typically used beyond building and customer analytics, but there's a lot of potential in using smart meter data. When it comes to taking action, there's not, just doing some customer analytics doesn't really improve the operation of a utility, so they don't take any tangible action out of this data. So to address this, we have developed different tools using smart meter data that can help utilities analyze the data better, as well as take better action with this data. So the objective of the project is to develop data-driven tools to help utilities plan and operate their assets economically and efficiently. So to this, there are going to be like different data sets. We're going to explore that are different data sets available with utilities, and the different data quality requirements for this asset management tool that we have developed. So we're going to look at type of data sources, the time granularity required for a good estimate of this asset management, as well as different bad data issues. So before I jump into the tool itself, I'm going to briefly describe the data set that we utilize. So this data is obtained from a utility in North Carolina. It's in Boone, NC, if you're familiar with North Carolina. It's up in the mountains. So it's a winter peaking load being in the mountains, and being a small utility, this is a lightly loaded circuit, so you don't see any voltage or power factor issues on the circuit. But it's 100% deployment. So the customer mix is typically residential and commercial customers. The utility serves through 5 substations serving 8,700 smart meters or customers through 1,400 distribution transformers. So there's a wide variety of these transformers from like 5 kVA to 1,000 kVA. And the data is over 3 years because the AMI was installed in 2017. And then the number of data pills. So the smart meters collect a lot of data. So it's reflected here. About 42 data points are collected by each smart meter. And the time granularity of the data is around 15 minutes. So the data processing initially, what happens is we got 3 years of data towards that, later off of 2017 to December 2020. So all the smart meters were combined together in each year. So the first step was to, extract the individual smart meter profiles from these. And as I talked about, there are 42 data fields available with each smart meter. So we just chose these 7 data fields for our analysis. So that's all is required for asset management. For distribution transformer perspective. But there are other data points like voltage, current that can be used for other purposes. So the main data point or data field is kilowatt hour, which is actually recorded as a running sum. So every 15 minutes, the energy usage is added to the previous value. And so you will see a linearly increasing curve on each smart meter. Now the EKW is the average kilowatt power usage by the customer in 15-minute interval. So this is this is what we are trying to achieve, and it's already been recorded in the smart meter. But turns out there's a lot of missing data in this EKW. So what we do is we take a running sum on the kilowatt hour to eventually get the usage, 15-minute usage, and we just use the EKW to compare or validate our extracted data from kilowatt hour. So the first step is to do bad data correction. For if you are in the industry, when you collect data, you come across bad data issues. It's very typical to draw data points. From the perspective of smart meter, these are the different data issues that we saw. So missing data points, bad data points like outliers, daylight savings time. Not many people talk about it, but this is also a very tricky because smart meters are not aware of daylight saving time jumps. And then there could be missing timestamps like missing data points. These are generally caused by communications issue in the AMI system and like smart meter processing errors. So data is stored in the smart meters and then it's only communicated every 15 minutes. So there could be a lot of issues that happen in between that lead to these bad data issues. So from the challenges in addressing this, all the public data sets are usually clean data. But when you start working with raw data, you'll realize that this is going to be the most time-consuming part of the data analysis project. You could start with a small sample of data, but the issue is you won't see all these bad data issues in the small sample. So we used an October month data from 1 year to do our initial prototype of the analysis, but we didn't see any of these bad data issues in that 1 month. And the third trick is there's no universal tool to this. It depends on data set to data set, utility to utility, how they store the data. So all these factor in. So you can't develop one tool to address all the different issues in different utilities. But why is this really important is because later on we are going to see we develop transformer temperature models, which is highly sensitive to bad data. So you need to, even one single bad data can really skew our analysis. So we need to clean or address these bad data issues before we proceed with our analysis. So here are a few examples of the bad data issues. You can see, as I talked about, the kilowatt hour running sum is our primary data point. You can see that could be random resets like this. And for no reason, the smart meter profile decided to go to 0 and then start tracking again. There could be random spikes like this. This is impossible to achieve by a single customer because this kilowatt usage could be somewhere in 10,000 to 100,000 level, which in 15-minute interval, no customer can put this amount of power. Similarly, there could be random dips like this. So you can clearly understand these are data processing or communication issues. Now, this was really interesting. So what happens here is I think at 100,000 limit, smart meters tend to reset the value back to 0. And later on, after discussing with the vendor, we understood that the smart meters don't have enough memory to store data values above 100,000. So what they do is they simply go back to 0 and start tracking again. Even though this is not this is predictable because at what value this can happen, but still this is hard to understand if you have never worked with smart meter data before. And the final is it could be a combination of all this, so that becomes even more trickier to address these bad data issues points. Now, I'm not going to talk about how I addressed all these data issues in this presentation because we have more interesting stuff to get to. So I'm going to point to our paper that we recently published where we discuss about different data issues and how we have addressed them, different algorithms to address different data issues here. So, but this is the basic processing workflow, step by step, how you address each of these issues before you finally end up with clean smart meter data. So once you have the smart meter data, the goal is to develop the transformer profiles, transformer load profiles. And for this, we're going to make use of GIS data available with utilities. So this geographical information, what it does is it maps it provides the mapping between the installed transformers and the installed smart meters under them. So basically using this information, we can simply add the load profiles of these smart meters together to eventually get our transformer profile. This is just straightforward addition. So you will end up with a real power profile of the transformers. But to proceed with the analysis, we need actually the actual KVA profile of the transformer, KVA usage of the transformer. So that incorporates reactive power as well. Since it is not recorded by all the smart meters, what we do is we use the substation power factor data that is available from SCADA measurements. And we make an assumption that all transformers under a substation will have the same power factor. Using that assumption, we can come up with the KVA data of each transformer. So our second tool is transformer overloading analysis. And the trick here is that distribution transformers are designed to be overloaded beyond nameplate rating. So you cannot simply use the load profile compared to the rating to decide if the transformer is overloaded or not, because they have been designed to be overloaded, but overloading the transformer beyond a certain degree comes with the risk of failures. So the detailed implications of risk of overloading oil immersed transformers is provided in these two standards, an IEEE standard as well as a European standard. They both address the same issues, but using different mathematical models. So basically what we're going to use this standard for is that we're going to use the mathematical developed here, which actually calculates the transformer internal temperature using the transformer loading and the ambient temperature profiles. So what are these transformer internal temperatures? So you can see this is the thermal diagram of a transformer. These are the these are radiators. You can see the core here, the winding wound around the core. But of all these temperatures, we are interested only in 3 of these temperature. One is the ambient temperature that surrounds the transformer. This can be different from what we realize because some transformer installations can be underground as well. And then there is top oil temperature. The oil at the top of the transformer, the temperature of that is top oil temperature, which is given by theta TO. And then there is also a temperature associated with the winding. Generally, it is hotter than the top oil temperature. So we indicate that using theta H, which is winding hotter spot temperature. Now, these temperatures, apart from ambient temperature, they're also affected by the loading on the transformer, which is indicated by this delta theta TO. So this is the rise of top oil above the ambient temperature due to the loading on the transformer. And this is a really involved mathematical model involving exponential terms and different parameters of the transformer, both these values. So we are not showing that formulas here, but you can refer to the standard or a paper for the complete model of these temperatures. So, but the basic idea here is that both loading as well as the ambient temperature is going to affect the top oil and the hotter spot winding temperatures. Now, this winding temperature, after a certain degree, is going to affect the insulation life of your oil, which is going to degrade the actual age of the transformer, which is given by FAA, which is the equivalent aging of the transformer. Now, you'll understand how this accelerated aging works in our next slide. So here's a plot of the, a brief profile of loading of one of the transformers. This is given in per unit. So anything above 1 per unit means that the transformer is overloaded above nameplate rating. Now, these are the top oil and the hotter spot temperature variation according to this loading profile. You can see 4 factors affect the final temperature, hotspot temperature. One is ambient temperature. I don't show it here because it's very trivial. Higher the temperature, higher the impact on the internal temperature. But the other factors are the peak overload. You can see at the instance when it hits the peak load, you can see the temperature starts to rise significantly high. And the second factor is how long does this overload last? Depending on that, you can see a further increase in the temperature. And the third thing is, I don't have an example to show in the actual data, but you can see, let's say if another overload happened quite consecutively to the previous overload, then that can lead to a further increase in the temperature. So the duration between the overload also affects the transformer temperature, which in turn is going to affect the age of the transformer. So what do I mean by transformer accelerated aging? So according to the standard, when theta H is constant at 110 degrees Celsius, your transformer is going to age 1 day on a natural 24-hour period. So your transformer is going to lose 1 day of life on a 24-hour period, which makes sense. But once the temperature goes above 110 degrees Celsius, depending on the magnitude of this temperature, you're going to have accelerated aging. What this means is in a 24-hour period, your transformer can age either 2, 3, or 5 days, depending on how high does this theta H go, which is in turn related to the loading and the ambient temperature.
Vali,
yeah.
Why did you pick 110C?
So this is developed from thermal models by the standard. This is according to the standard. So they have done a lot of testing with actual transformers during the manufacturing phase to identify that the normal aging happens at 110 degrees Celsius.
And that's dependent upon the oil type, perhaps, in the transformer?
Yeah, so generally right now, there is a rating for the oil that says 65 degrees Celsius rise above. So either it's 65 degrees Celsius rated or 55 degrees Celsius rated. I think after 1970, all of the transformers installed were 65 degree rated rise in temperature. So for all those transformers, this is the actual aging limit for the transformer.
Okay, that was a question from the chat. Thank you.
Thank you. So, apart from aging, there are other risks of overloading. So, for instance, if theta TO reaches above 120 degrees Celsius, you can have oil expulsion. So this is top oil, so it's going to expand significantly. So it's going to expel out of your conservator. Once the oil cools down after the overload event, your oil is going to contract, which can lead to exposed electrical components. So which can cause increased probability of failure. When theta H rises above 200 degrees Celsius, this is quite an extreme overload. Under this, you can have significant insulation breakdown in the oil, which can lead to increased probability of failure. I talked about if theta H is quite significantly higher than 110 degrees Celsius for a long duration, it can lead to accelerated aging, which can reduce the useful life of transformer. The fourth point is above 140 degrees Celsius, even though it doesn't lead to immediate failure, you can have bubble formations inside the transformer. So this is going to increase the moisture content in the transformer oil, which can eventually increase probability of failure. And the final one, this is very difficult to achieve, but sometimes if your per unit loading, which is absolutely high, 3 per unit, 3 times the rating, if you load the transformer at such a high rating, it can affect the auxiliary components, not just the oil, but anything that is put on top of the transformer, like bushings and other factors, can be impacted, which also increases the probability of failure. So all this, what does it imply is just monitoring the load alone is not sufficient, because you have to build these internal temperatures from the load to understand what is the risk of overloading the transformer. And utilities actually try to change the customers from one transformer to another, depending on necessity that arises, due to some change in new lines. This happens a lot. Topology change, customer change from transformer to transformer, nearby transformers. This happens a lot. So you need to monitor the transformers frequently to understand how they are overloaded. And also, given a smart meter, the customer under that smart meter can change. A lot of apartments, people change from year to year. So their usage pattern, a residential customer can become a commercial customer. They don't intimate the utility. So that can also have an impact on the load profile of the transformer. So for all these reasons, you need to keep frequently monitoring the temperature and understand how the overloading happens. So basically, this is our tool. We are going to use the ambient temperature data, which you can easily get from a nearby airport. Utilities don't record the ambient temperature data. But then it is available readily with weather stations and airport. You use the smart meter data to build the transformer load profiles with per unit loading. And those temperature models, they involve a lot of parameters specific to the transformer, like size of the transformer, weight of the transformer, oil capacity. So all these can be obtained from nameplate rating. So this is like a metadata available for each transformer. So using all this information, we'll build the top oil temperature, and then finally build the hotspot temperature, come up with the accelerated aging. Now, different transformers can be installed at different timelines. So their service timeline is different. So for that case, you want to normalize this accelerated aging based on the life of the transformer. So that is given by equivalent aging. So it normalizes the accelerated aging parameter. Now, based on this equivalent aging, we'll rank the transformers based on how severely overloaded they are, because this equivalent aging is going to really translate back to the extreme overloads in the transformer. So this is our equivalent aging. As I talked about, it's a normalized value in per unit. You can see this is how we rank the transformer. Transformer 2 seems to be most overloaded, then comes transformer 1. Now, to compare this with a base strategy, what we do is, if we have just the load profiles, we can still basically understand how high is the loading on the transformer above rating and add them together to get a value called overload energy. Now you can rank the transformers based on this overload energy as well. Now you can see transformer 2, which is most overloaded in our proposed strategy, is only is only ranked number 2 in our base strategy. And this is primarily because the overload energy does not capture. So it does capture two things. One is peak overload, as well as duration of overload, because that comes into energy value. But it does not capture the duration between overloads. So that is also an important factor which is being considered in the proposed strategy. So let's look at this overloaded transformer, which is transformer 2. Now you can see the hotspot temperature profile of this transformer 2 and the loading profile. So this red line here is the rating of the transformer, which is 15 kVA. Now you can easily see it is sometimes overloaded up to 3 per unit, and consistently overloaded in the winter up to 30 kVA, which is 2 per unit. Now this is significant overloading on the transformer, which is reflected on the hotspot temperature, because you can see whenever this is violating, which is significantly high, it goes above the normal aging value, which is 110 degrees Celsius. And sometimes it also extremely violates this 200 degrees Celsius, which is the breakdown limit that I talked about before. But one good question that you might have here is that, if the transformer is violating this temperatures these many number of times, then it should have failed already, right? But turns out predicting the failure of transformer, that's why I mentioned it's not, increased probability of failure, but not actual failure. Because transformer or predicting transformer failure is really difficult. Even IEEE standards, make it explicitly clear that predicting transformer failure is really difficult, because we are only looking at loading impact on the transformer, but transformers can fail to multitude of other reasons, like moisture content around the transformer, bushing failures, auxiliary equipment failures that are not related to just loading on the transformer. So for these reasons, you can only predict that this is higher probability. So, even though this transformer has not failed, but, in near future, it is going to fail. So the utility has to pay more attention, decide whether to replace this with a higher rating to avoid these overloads. Now, the transformer 1, which was rated number 1 in the base strategy, actually does have overloads. You can see it is about 2 per unit in 2018. But then the temperatures don't rise that significantly high, like we saw in the transformer 2. And basically, there is also this issue where there has been a change in customer around 2018 September. So the transformer is not overloaded anymore, which is also impacted in the temperature. But from a utility perspective, what they can do is they can change this equivalent aging strategy from an overall 3-year period to a yearly analysis, so that now you can easily see that the transformer 1 was overloaded in 2018, but then it is not overloaded anymore in 2019 or 2020, which is due to the change in customer. So basically, the utility does not have to worry about transformer 1 anymore, because it is not overloaded anymore, so they can simply continue using the transformer. But overall, out of all the 1,400 transformers, we could only find these 2 transformers that were overloaded. The other transformers were not even considerably overloaded at all. And that's primarily because, as I pointed out, this is a lightly loaded circuit, so you don't see that many overload on the transformers. So as I pointed out, this overload, there are only few transformers in the circuit. So, but then the utility was interested in another factor where they realized that they could save a lot of money, which is underloaded transformers. Underloaded transformers are these large apartment transformers, serving hundreds of customers, so hundreds of smart meters under dome. But then, due to bad planning, sometimes these transformers can be severely underloaded. So, for instance, this is the efficiency curve of a 750 kVA transformer, which is an apartment transformer. It's serving 83 customers. You can see from the efficiency curve, it is clear that transformers are efficient devices. For most of the loading per unit, the transformer efficiency is close to 100%. But then during low loading region, below 20% loading, the transformer efficiency falls quite drastically. And the other factor is, even if you overload the transformer, which comes with some risk of failure, it still doesn't eat into the efficiency of the transformer. You can see it's still close to 100%, even though it's slightly reduced. The efficiency is still close to 100% during overload. So here the inference here is, it is better to overload the transformer if you properly consider the severity of overload. rather than just underloading the transformer, which can end up as big loss for the utility. Because these underloaded transformer, the main reason for this fall in efficiency is because they are supplying a lot of no load losses without supplying any load losses. Now, all these losses are not, the customer does not pay for these losses. Utility has to pay for all the losses in the circuit because they fall on the primary of the customer. So for this reason, utility is really interested in reducing these kind of inefficient operation of the transformers. You want to, obtain the best utility for these largely rated apartment transformers. But then let's say if you want to reduce the size of this transformer from a large transformer to a smaller transformer, they come with a risk of overloading, because once you reduce the size, you have to consider this risk of overloading in your analysis, because you cannot control the customer load. You can control only the size of the transformer that you replace with. For this reason, what we propose is a search-based algorithm where we obtain the current type and phase of the transformer. Type is the mounting type, because if it is a pad-mounted transformer, you can only replace it with a pad-mounted transformer. Utility is not going to replace it with a pole mount because it requires a different infrastructure altogether. Now, you have to consider that. Once we consider that, we use the, we start reducing the size, comparing the search criteria here, where we make sure that the transformer temperature, the new rating that we propose, it doesn't violate these risk considerations. And once we do this, we propose, finally we propose the utility 3 different ratings, so that the utility can choose any one based on the availability in their transformer yard or in the stock. Since you can understand that this is a planning-based problem, you have to be make sure this is robust enough considering unforeseen events. From a winter peaking load perspective, these unforeseen events can be like, when there is a lot of heating load, you can have cold load pickup issues after a brief fault. You can also have unforeseen extreme weather events. There's a lot of winter storms happening in Texas recently. So you're starting seeing cold weathers that you have never seen before. And you have to consider that the overloads caused during those intervals, your transformer rating can sufficiently handle those overloads. So from cold load perspective, cold load is nothing but once a fault happens, all your customers under a transformer lose their diversity. So you're going to see significantly high load immediately after you pick up the customers, which then will fall back to the normal value after certain duration. So this is technically what a cold load pickup is. And it's easy to simulate using an exponential model. For details of the model, you can refer to the reference here. But instead of using the 3-year smart meter data, we are simply going to simulate a cold load pickup event on top of, we use the 3-year data, extract the peak load on this data to be conservative. And on this peak load, we assume that as the pre-fault load, and we introduce the cold load pickup event. Now we simulate a 24-hour profile, and using this profile, we'll again do the search-based analysis that I pointed in the last slide to come up with 3 different ratings again. For extreme weather, I've put an average box plot of every daily temperature profiles in Boone, North Carolina for the past 10 years. So we are ranking them based on average, minimum average. So you can see these are really negative values. So these are the dates where the temperature has been the coldest in Boone, North Carolina. So you can see we have the data, low data from 2017 to 2020, but most of the cold load events happen in 2014. But we don't have the low data for these events. So we cannot make sure, the transformer would operate without any risk of failure, even during these cold load events. To address this, what we do is we try to build a transformer load versus ambient temperature model, so that based from the available data, so that we can predict the expected load in these cold load event days in 2014. So there is 2 different types of cold loads. One is like where the mean extreme weather, where it's more tighter box plot, so you can see throughout the day the cold weather is close to negative. But then there are days where, it can have a wide range from starting from 0 to really cold weather. But then the coldest weather here is around -20 degrees Celsius, which is much colder than 2014 January 7. Turns out mean peak weather has much better impact on the load rather than peak load weather. So we ended up using the mean extreme weather for our analysis. To build a transformer load versus temperature model, what we do is, we first look at the relationship between the temperature and load. So the blue line is at your blue line is your ambient temperature in Boone NC, and then the red line is the actual load profile from one of the transformers. You can see there's a negative correlation. So at coldest weather, the load is really high. So there's a negative correlation during winter months. And even though it is really hard to see here, you can see there is a little bit of positive correlation between summer months between the temperature and load. You can easily understand this from the scatter plot between the energy and the temperature of the transformer. You can see in winter months there's a negative correlation, and in summer months there's a small positive correlation. But as such, if we try to build a model for this, you can see it's a nonlinear model. You might need sophisticated algorithms like neural networks to build a efficient model for this. But to make it really simple, what we realized is most of the peak load happens in winter months. So we are just interested in understanding what is the relationship between load and temperature only in winter months. So if I plot out the relationship only in winter months, we can see there's a clear linear relationship between them. So we end up fitting a linear model for this case. You can see this is the black line is the linear fit, and the red and green line are the 95% confidence interval. So most of these scatter points lie within these curves. R squared is a value that we use to estimate the accuracy of this model fit. So it lies between 0 and 1. If it's closer to 1, then we have a perfect fit. You can see since it's a high value, this is a perfect fit, and you can also realize from the diagram. But then once we start fitting this for all the transformers, underloaded transformer, we realize that most of the around 92 transformers don't have a really good linear fit. So this does not mean that the model is not performing well, but this is simply just that there's no temperature dependence between the load and the ambient temperature. So there's no dependence between these two values. So in these cases, we can simply ignore the model because there is no impact of this ambient temperature, especially during the extreme weather. So it's not going to affect your load at all, and you don't have to worry about the rating of the transformer for those particular transformers during extreme weather. So again, we'll build a 24-hour profile for January 24 based on this January 24 temperature data. So you'll select the temperature points, get the load value, build the load profile, and then you'll again carry out the search space type criteria that we proposed earlier, and then you'll come up with the rating of the transformer. So here we summarize all those results together. The blue bar that you see here is the installed rating of the transformer. So it's already really high. Now the green plot is the search-based rating that you propose based on the 3-year data that you already have, smart meter data. The red line is based on the extreme weather, and the purple bar is based on the cold load rating. Now, when a utility is choosing a rating based on these 3 analyses, you'll simply choose the highest rating from all the 3 values put together, because that is most the conservative rating. It's going to be safe for all these different considerations. So the maximum value is highlighted using this purple line over here. So this is your proposed rating that you want to replace the existing rating with. Now the existing rating is also plotted on black line over here. So you can see throughout for pad mounted transformer, these are really big transformers. You can see the rating is about 225 kVA and can go as high as 1000 kVA. You can see there's a considerable reduction in the transformer size for these large transformers, and it becomes more pronounced when you go to really big transformers like 500 kVA and 750 kVA. You can see there's a huge reduction in the transformer size. Now, similarly, if you look at smaller transformers, which are like pole mounted transformers, you can see the rating is already installed rating is around 75 to 100 kVA. These are not big transformers, and you can see sometimes your proposed rating can go above than what you already installed for smaller ratings. And you can also realize that the saving that we propose, it's not significantly high, so it may not make economic sense to replace these transformers. So I mean, I already talked about the first 2 points, but then you have to understand the utility will not start replacing the existing transformer until it is required at some other place. You're not simply going to replace the 500 kVA with 100 kVA and just put that 500 kVA in your transformer yard sitting ideally. You want to make use of that 500 kVA. So until there's a use for that 500 kVA, you're not going to replace that transformer. You have to understand that utility also will not purchase that new transformer. Let's say you want to replace with 100 kVA, then you're not going to purchase that 100 kVA. It should be already available with stock, already available in your stock. And then the third important criteria here is that not all replacement will make economic sense. Okay. Just because there's a reduction, it may not make an economical sense until you actually understand what is the cost behind each of those values. So that's what we're going to look at in our next tool. And the primary reason, because it is affected by the transformer age, which you'll see later. So the final tool is cost-benefit analysis. And for cost-benefit analysis, we develop a total ownership cost. Okay, first of all, what we propose is we are trying to reduce the transformer size from 500 kVA to, let's say, 100 kVA. So what this happens here is that you are reducing the core size from a bigger transformer to a smaller size. So you're going to decrease the no load losses. But at the same time, you're going to also increase the loading on the transformer, because you were operating in that low efficiency region. Now you're going to operate at a higher efficiency region, but you're going to also increase the load losses in the circuit. So there's no clear understanding here, right? There's a give and take between these two values. So until you put a dollar value for these no load and no load losses, you cannot clearly understand what is the benefit of replacing a bigger transformer with a smaller transformer. So to do this, we are going to use total ownership cost. This is very famous with the industry, especially while utilities are bidding for a new transformer, they use this total ownership cost to make a decision on which vendor to go with. So the total ownership cost, it involves a purchase price, which is very trivial, the transformer price as well as the labor costs involved in installing the transformer. And then you're going to put a dollar value for the no load losses as well as the load losses. Now, this dollar value is going to depend on the age of the transformer, which is very critical. And it's also going to be impacted by the electricity price with escalation, because this is a life cycle analysis over the rest of the age of the transformer. So it is going to involve an interest factor as well as a price escalation factor. So yeah, the transformer age, let's discuss about that. There's an existing transformer. You're proposing to replace that with a new transformer. Now, both the transformers would have been already aged because this is already in service, and your replacement transformer is already sitting in stock. It is not newly purchased. So you're going to carry out the analysis for the rest of the useful life of the replacement transformer. So that makes sense. And here we make an assumption that the life of all transformers is assumed to be 34 years, because this is suggested by North Carolina Utility Commission. Now, the reason why we make this assumption and not actually try to understand the actual age based on loading factors and other things that I pointed out earlier is because it's very difficult to predict useful life of a transformer. You can only predict equivalent aging, accelerated aging, which are just a relative parameter, but not an absolute age, because it can, as I pointed out, the transformer can fail due to multitude of reasons. Now, based on this age, there are 3 different cases. Case 1 is where your existing transformer is much older than replacement transformer. Case 2 is where it's much newer than the replacement transformer. And the third case is where they both have same age. Here, the analysis is trivial because you just want to replace the new transformer, existing larger transformer with a smaller transformer. But we're going to look at these 2 cases in detail. So when the existing transformer is much older than replacement transformer, what will happen is, since you're going to run this life cycle analysis for N2, which is greater than N1, Before the end of this analysis, if you just decided to replace, without the knowledge of this replacement technology, the rating that we proposed earlier, we don't have this knowledge, the utility what it have been doing right now is, once this fails, it'll just replace that with a new 500 kVA transformer. Since it's based on N2, at the end of N2, this new transformer will leave behind the depreciated value, which is a saving for the transformer because you can use this transformer even beyond this N2 value. So basically what happens here is when T1 is greater than T2, you would end up buying a new transformer in existing case, in a base case analysis, instead of replacing with a replacement strategy. So yeah, I think it'll be more easy to understand here. Let's say T1, we take a consideration where 500 kVA transformer is replaced with our proposed strategy from earlier, 112.5 kVA transformer. And you can see N2 is 14 years. And that's because we assume that T1 is greater than T2. We don't purchase this new transformer, the replacement transformer because it's already available in stock. But then there is a depreciated cost for this because you already purchased it a few years back, 20 years back. So this is the actual cost of this transformer right now. There is a labor cost associated in installing this new transformer. These two values are because you install this again at the end of N1 for this 500 kVA transformer. You can see the no load losses are higher for 500 kVA. So eventually the no load cost is higher, but the loading is higher for 112.5 kVA. So your load losses, cost of load losses is higher here. But once you add all these values together, this value is the depreciated cost. So this is the saving from this new 500 kVA that you installed. So once you add all these together, you get the total ownership cost. And when you subtract these two values, you get something called net present value. So if the net present value is positive, then it makes sense to replace this existing transformer with a new transformer. And if it is negative, then it doesn't make any sense to replace existing with a new transformer. Now you can see it is a positive value, but this is bare minimum because it's close to the labor cost that is involved in installing this 112.5 kVA. So basically, there is absolutely no saving in replacing the transformer other than just releasing this 500 kVA for some other use. So this no significant saving is realized because there's only 14 years of analysis left in this new transformer that you decide to replace with. Now, for instance, if this N2 was higher, the new transformer that you decide to replace with has higher remaining useful life. In that case, you can see that there is a significant amount of saving, around $5,000 saving. So whenever N2 is large, given that T1 is greater than T2, you're going to see a significant saving in replacing the transformer. Similarly, case 2 is where existing transformer is much newer. So in this case, what will happen is you won't even completely use your existing transformer by the end of the replacement transformer. So you're going to leave behind a depreciated saving from the old transformer without even purchasing a new one. So basically, similar analysis, you can see you're not purchasing a new one anymore. There's a saving by the release cost. But then once you add all these values together, you realize that the net present value is significantly negative. So what this means is that even though there is a significant reduction in the transformer size, if the new transformer that you choose to replace with has a considerable age, like 30 years here, then it doesn't make any sense to replace this transformer, even though there's a large reduction in rating size. So as a tool for a utility, you're going to already have the transformer ID, existing transformer ID. The proposed rating, either you can choose a random value based on your available stock, or based on something lower than the existing rating, or you can use our previous analysis, underloading transformer analysis, and if that transformer size is available, then you can use that size. But then the size availability alone is not a factor, but the age of that availability. So this is a case-by-case basis. You don't know in prior to the analysis what is the age that you already have in your yard. So this becomes a user input value. So you can decide between different 100 kVA transformers with different ages to see which one provides the most positive net present value, which indicates there is a benefit in replacing the transformer. So as a toy example, what I do here is these are all the different pad mounted transformers, and the rating that you see here is the replacement rating from our previous analysis for the existing rating. The existing rating I don't show, but you can see these are 300 kVA transformers, these are 500 kVA transformers. They have been decided to replace with 50 to 70, 100 kVA transformers. So if I assume that I'm going to replace all these existing with this proposed rating, and all the proposed rating, let's say, have 10 years of remaining life, you can see only some of them provide net present value, positive net present value. And if you decide to replace all this, there are only 38 positive net present value. And if you decide to replace all these transformers, then you'll end up with a saving of 104,000. So if I do this analysis for different mounting types, you can see only the pad mounted provides the maximum benefit. And the number of replacement also where you get a benefit is also higher for pad mounted. But overall, you can see that the utility can potentially save $200,000 just by replacing all this existing rating, but it comes at a big assumption that I already proposed earlier. But then it still just shows that what is the potential saving a utility can do with a small size. I have to highlight here this utility had only 1,400 transformers. And with that small set, you can create a savings of about $200,000. So there are two ways the utility can use this tool. For a given existing transformer, and you see, let's say 500 kVA is supposed to be replaced with 100 kVA, but you have 5 different 100 kVA transformers in your stock. This will let you choose a particular 100 kVA transformer depending on the age and the most benefit that you get from the net present value. You can flip this other way around, where you have a range of 500 kVA transformer. That is, so you need a 500 kVA at some other location, but there's a range of 500 kVA transformer underloaded already installed. But you want one of these transformers, and you have a replacement transformer in your stock. So you can decide which of these 500 kVA transformer that you want to replace with, which gives you the most benefit. So to summarize, we have developed 4 different tools addressing different factors for the distribution transformers. We even provide a cost benefit tool to realize what is the benefit of undergoing this replacement that we propose. So, and we also address the data quality, data requirement issues for complete asset management based on existing infrastructure. We don't use any, we didn't go install any new sensors or any data points in the utility. So these are some of the references you can refer to, and that actually concludes my presentation. So thank you so much for paying attention. And if you have any questions, I'm happy to stay back and answer your questions.
Thank you, Vali. We did have a question from the chat.
Sure.
The aging model of the transformer is basically based on the hotspot temperature, but it's known that there are other factors. Did you consider some of these other factors like electrical aging, like partial discharge or other things? How would that influence your study?
So we don't really use that. Apart from loading, we don't use any of these other factors that is mentioned. So it is a very interesting topic. So there are factors like harmonic discharge, partial discharge due to faults and other reasons. But the issue is these are, you said when it comes to, I think I'll go back to my first slide. So you have dedicated devices on power transformers, which actually, look at dissolved gas, which look for partial discharge in your transformer.
Full screen? Yeah.
But then you need special sensors and much smaller granularity to, include all these factors in the transformer. But then, if you look at it, unless it's like 500 kVA or some 50 kVA above, utilities are not really interested in being that conservative in analyzing all of these factors. If they just need an indicator to see if this is significantly overload, if I can avoid this, I'll go and make like replacement. But right now the practice is not to look at all the factors that affect the distribution transformers.
So what you've done is this is the way to use data that you're already collecting versus the expense of adding additional sensors to these lower rated transformers, to the distribution system, right?
Exactly. So for instance, if you want to look at harmonic, you need much granular data. So you might want to revert to micro PMUs, but you cannot install micro PMUs on all these devices. They only install at selected places. So yeah, they require different type of data, different sensors. So we don't look at those here.
Okay. And this was, again, the source of your data was AMI information at the customer meter, right?
Exactly. So this utility had 100% AMI deployment. So that was very beneficial, but the primary data set is the AMI data, but revolving around that, the different data sets like GIS data, SCADA data from utilities were just used to improve the analysis, but primary data set is smart meter data set.
Yeah. Terrific. Well, we are right at the end of our time. I appreciate everyone for joining us. Know that Vali's information was there in that last slide, and we did record this webinar, so everyone who registered and attended will receive a link to that recording when we post it to the NC State Electrical and Computer Engineering YouTube channel, and I'll send that out probably next week. Vali, thank you very much.
Thank you, Ken. Thank you, everyone.
All right, we'll end the webinar now.